go in this lecture and answer two questions. In the first question, we find out the perimeter of this quadrilateral ABCD. And in the second question, we find out the area of this green shape. So we start with the first question. In the drawing, we have quadrilateral ABCD. We know that AP equals to PQ. This is line 7 PQ. It equals to 10 units in its length. This is line 7 PQ. It equals to 20 units in its length. This is line 7 QC. This equals to 4 units in its length. Those three angles are all right angles. Again, our task is to find out the perimeter of this quadrilateral ABCD. So, first of all, what is a perimeter? A perimeter of a quadrilateral is the sum of its four side lengths. That is to say, the perimeter of quadrilateral ABCD equals to AB plus AD plus DC plus CB. So, in the first step, we will do a construction. That is to say, we will draw perpendicular on AD at point P. Again, we will draw perpendicular on AD at point P. So actually, this angle equals to 90 degrees on its side, and this angle also equals to 90 degrees on its side according to our construction. In the next step, we'll extend the perpendicular from point P by a straight line until it touches side BC. And we define the touching point of the extended perpendicular from point P and BC. This point is point M. Here we can implement all 18 in our drawing. We click quickly on all 18. According to all 18, if the sum of two one-sided interangles is equal to 180 degrees, then they lie between parallel lines. So in the drawing, we have those two angles alpha and beta. They are both defined as one-sided interangles. So if the sum of those two one-sided interangles is equal to 180 degrees, that is to say if alpha plus beta equals to 180 degrees, then they lie between parallel lines. That is to say, then line A is parallel to line B. So any two one-sided interangles that and the sum of them is equal to 180 degrees, they must be located between parallel lines. In this case, if alpha plus beta equals to 180 degrees, then line A is parallel to line B. So we can implement all 18 in our drawing. In our drawing, those two angles, they are both defined as one-sided interangles. The sum of those two one-sided interangles is of course equals to 180 degrees. Therefore, those two one-sided interangles are located between parallel lines. That is to say, AB is parallel to PM. So, until now, we found out that according to all 18, AB, side AB is parallel to line 7 PM. Likewise, the sum of those two one-sided interangles is also equal to 180 degrees, and therefore those two one-sided interangles must be located between parallel lines. That is to say, PM is parallel to DC. PM is parallel to DC according to the same rule, all 18. And finally, the sum of those two one-sided interangles is also equal to 180 degrees, and therefore according to rule 18, those two one-sided interangles are located between parallel lines. That is to say, AB is parallel to DC. Here we have AB is parallel to DC according to the same rule, rule 18. Those three parallel lines, that is say AB, PM and DC, they are connected together by line segment AD and by this line segment BC. Again, AD and BC connects the three parallel lines together by straight line. And whenever you have three or more parallel lines that are connected together by two other line segments, then you can implement the basic proportionality theorem. The basic proportionality theorem is about the relationship that exists between the two line segments AD and BC that connects those three parallel lines together. And the relationship is as follows. So according to the basic proportionality theorem, a special relationship exists between AD and BC. The relationship is as follows. AP over PD equals to BM over MC. Okay, again, according to the basic proportionality theorem, a special relationship exists between AD and BC. The relationship is as follows. AP over PD equals to BM over MC. AP equals to PD according to what is given in the question. So if you define the length of AP as x, then PD must be also equal to x because they are equal to each other, according to what is given us in the question. So AP over PD is x over x, and x over x equals to BM over MC. X over x is 1, so 1 equals to BM over MC. Here we will multiply this equation by MC, and finally we get that MC equals to BM, or BM equals to MC. So if you found out that this is line segment BM, this equals to line segment MC. If BM equals to MC, it means that point M is the midpoint of BC. Again, if BM equals to MC, it means that point M is the midpoint of BC. That is to say, at point M, BC is being bisected into two halves. The first half is BM, the second half is MC, and each half has been equal, of course, to BC over 2 because BC has been bisected into two halves. So, I'll write it down. If you found out that the first half of BC is BM, and it is of course equal to the second half of BC, that is MC, and each half equals to BC over 2 because BC is being bisected into two halves. So again, from going to reality, first of all we found out that BM equals to MC. BM is the first half of BC, and it is of course equals to the second half of MC. Each half must be equal to BC over 2 because BC is been bisected into two halves. So what is the value of BC? BC in total equals to BQ, that is 10, plus QC, that is 40. So in total, BC equals to 10 plus 40 over 2. 10 plus 40 is 50, and 50 over 2 is 25. So from this long equation, we will derive that Bm equals to MC equals to 25. That is to say, we found out that this is line segment Bm, that is equals to 25 units in this line. And it is equals to this line segment MC, that is also equals to 25 units in its length. In the next step, we will do another construction, that is to say, from point M, we will draw perpendicular on DC. Again, from point M, we will draw perpendicular on DC. So roughly, this angle equals to 90 degrees in size, and this angle also equals to 90 degrees in size according to our construction. We will define the touching point of the perpendicular from point M and DC. This point is point N. By doing this construction, we can do quadrilateral PM and D. Inside quadrilateral PM and D, we have 1, 2, 3 arteries. The sum of 3 arteries is 270 degrees. So 270 degrees plus the size of this 4 pieces angle, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4 pieces angle must be equal to 90 degrees in its size. So in quadrilateral PM and D we have 4 angles, and therefore quadrilateral PM and D is a rectangle. We already found out that Bm equals to 25, Bq equals to 10 according to what is given in the question. So the missing line segment Qm equals to Bm minus Bq. So Qm equals to Bm minus Bq. So in total, Qm equals to Bm, that is 25, minus BQ, that is 10. So in total, Qm equals to 25 minus 10, that is 15. Qm equals to 15 units in its length. This is line segment Qm, that equals to 15 units in its length. In the next step, we will implement the Pythagoras theorem on this right green triangle QPM. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this right green triangle QPM, here by PT is the version for Pythagoras theorem. So in this right green triangle PQM, PM squared, that is the square of the hypotenuse, equals to Qm squared plus PQ squared. And again, according to the Pythagoras theorem, this green right triangle PQM, PM squared, that is the square of the hypotenuse, equals to Qm squared plus PQ squared. PM is the missing hypotenuse, so we leave it as it is, so it is PM squared equals to Qm squared. Qm is 15, and therefore Qm squared is 15 squared, this is 225, plus QP square. QP is 20, and therefore QP square is 20 squared, that is 400. So in total, let's remember that PM square equals to 225 plus 400, that is 625. So if you found out that PM square equals to 625. Here we take a root out of this equation and find again that the length of the conus PM is equal to the square root of 625, that is 25. So this is the bonus PM that is equal to 25 units in its length. So in rectangle PM and D, the opposite sides are equal to each other. That is to say PM equals to DN, but PM equals to 25, and therefore the opposite side DN must be also equal to 25 units in its length. So DN equals to 25. In the next step, we will define this angle QPM, as alpha. So in this green right triangle QPM, this angle equals to alpha, this angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in a triangle. This is side BC of quadrilateral ABCD. BC is the side of a quadrilateral, it is absolutely a straight line. So if you focus on the left side of the straight line BC, at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of the straight line BC at point M, we have this angle that is equal to 90 degrees minus alpha, plus this angle that is equal to 90 degrees, plus this first angle. In total, the sum of those three angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to alpha. Why? Because 90 degrees minus alpha plus 90 degrees is 180 degrees minus alpha, and 180 degrees minus alpha plus alpha is equal to 180 degrees. That is the sum of the angles on the left side of the straight line BC at point M according to all three. So this missing angle is equal to alpha. So in this right triangle MNC, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha, according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we will prove that those two right triangles can go into each other according to angle side angle rule. That is to say, we prove that this is the green right triangle PQM, that is can go into this right lower triangle MNC according to angle side angle rule. So when those two right triangles can go into each other. First of all, those two angles are both equal to alpha, and therefore they are equal to each other. In addition, those two hypotenuses of those two right triangles are both equal to 25 units, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So I found out that those two right triangles can go into each other according to angle side angle rule. That is to say, that we prove that those two angles and the side that is included between those two angles is the first side PM, and this green right triangle PQM are corresponding equal to those two angles, and the side that is included between those two angles that is actually side MC, this lower right triangle MNC. Therefore, those two right triangles can go into each other according to angle side angle rule. So I'll write it down. If we found out that this is the green right triangle QPM. Incongruence. This is the sign of congruence. So this right triangle M and C according to angle side angle rule. Then again, I should found out that the right green triangle QPM congruent to the right lower triangle M and C according to angle side angle rule. And from the fact that those two right triangles congruent to each other, we will derive that those two corresponding angles must be also equal to each other and their lengths. According to the rule, it says that corresponding sides in congruent triangles are equal to each other. This is to say those two triangles congruent to each other, and therefore those two corresponding angles must be equal to each other and their lengths. But QP is 20, and therefore the corresponding side M and N must be also equal to 20 units in itself, according to the rule that I mentioned. Corresponding sides in congruent triangles are equal to each other. Likewise, those two corresponding sides and those two congruent triangles must be also equal to each other and their lengths. But QM is 15, and therefore NC must be also equal to 15 units in its length, according to the rule that I mentioned. So in total, DC equals to DN, that is 25, plus NC, that is 15. So 25 plus 15 is 40. AB is the missing side. And this is 97 PM. This is equals to 25 units in its length. This is quadrilateral ABCD. In quadrilateral ABCD, we know that side AB is parallel to the opposite side DC. Here AB is parallel to DC according to rule 18. And because of the fact that quadrilateral ABCD is one pair of parallel sides, quadrilateral ABCD is defined as a trapezoid. Those two parallel sides AB and DC in trapezoid ABCD are defined as the bases of the trapezoid, while AD and BC, the other sides that are not parallel to each other, are defined as the legs of this trapezoid ABCD. Okay, what is the definition of line segment PM? Line segment PM bisects the two legs AD and BC of this trapezoid ABCD. First of all, line segment MP bisects AD. Why line segment MP bisects AD? Because point P is the midpoint of AD. The first half of AD, side AD, equals to AP, and it is of course equals to the second half of AD, that is PD. And each half of course equals to AD over 2, because AD is being bisected into two halves. So in conclusion, you can say that line segment MP bisects the leg AD. Likewise, line segment MP bisects the leg AD. Likewise, the same line segment MP bisects the leg BC of this trapezoid ABCD. Why? Because at point M, BC has been bisected into two halves. The first half of BC is BM, that is 25, and it is of course equal to the second half of BC, that is MC, and each half must be equal to BC over 2, because BC is being bisected into two halves. BC is 50, so BC over 2 is 25, so each half of BC is equal to 25, you can see here. So in conclusion, you can say that 97 PM bisects both legs AD and BC of trapezoid ABCD, and therefore line 7 PM is defined as the mid-segment of trapezoid ABCD. Actually, trapezoid mid-segment theorem is about the length of this line 7 PM. According to the trapezoid mid-segment theorem, the length of PM equals to AB plus DC over 2. So PM, the length of PM is the sum of the two parallel bases of trapezoid ABCD. This is to say it is AB plus DC over 2. So I write it down. If you found out that according to the trapezoid mid-segment theorem, the length of this mid-segment PM that bisects the two legs AD and BC, the length of PM is equal to the sum of the two parallel bases of trapezoid ABCD, that's actually AB plus DC over 2. So again, we shall find out that the length of this mid-segment PM in trapezoid ABCD is equal to AB plus DC, that is the sum of the two parallel sides of trapezoid ABCD divided by 2. But we already found out that PM equals to 25, and therefore we'll substitute PM by 25. And it is equals to AB. AB is the missing side, so here it is. Plus DC. DC in total equals to DN, that is 25, plus NC, that is 15. So this in total equals to 25 plus 15, that is 40. So this equals to 40 over 2. So in total, if you found out that 25 equals to AB plus 40 over 2. Here we'll multiply the equation by 2 and finally get that 25 times 2 is 50. And it is equal to AB plus 40. Here we subtract 40 from the equation. Finally get that the missing side AB is equal to 50 minus 40 is 10. So here AB equals to 10 units in its length. This is according to the trapezoid mid-segment theorem, of course. AB equals to 10 units in its length. So the perimeter of trapezoid ABCD or quadrangle ABCD is equal to the sum of its four side lengths. That is to say, the perimeter of quadrangle ABCD equals to the sum of its four side lengths. That is to say, it is equal to AB plus AD plus DC plus CB. Repeat again, the perimeter of quadrangle ABCD equals to the sum of its four side lengths. That is to say, it is equal to AB plus AD plus DC plus CB. So the perimeter in total is equal to AB, that is 10, plus AD, that is 40. Here we know that in rectangle PM and D, the opposite sides are equal to each other. That is to say, MN equals to PD, but MN is 20, therefore PD is equal to X, also equal to 20 units in its length. Likewise, X here must be also equal to 20 units in its length. So in total, we found out that again AB is 10, AD is 20 plus 20, that is 40, plus plus CB again DC is 25 plus 15, that is 40, and AD is also 40. AD is 40 and this is also 40, plus CB. CB is 25 plus 25, that is 50. So in total, we found out that the perimeter of quadrilateral ABCD is equal to 40 plus 40 is 80, 80 plus 50 is 130, 130 plus 10 is 140 units. So the perimeter of quadrilateral ABCD is equal to 140 units in its length. And again, the answer to the question is that the perimeter of this quadrilateral ABCD is equal to 140 units in its length. In the next step, I present to you the second way to find out that AB equals to 10. According to the first way, use the trapezoid mid-segment theorem in order to find out that the missing side AB is 10. In the second method, we'll do another thing, that is to say from point B, we'll draw perpendicular on PM. Again, from point B, we'll draw perpendicular on PM. Okay, this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees in its size according to our construction. We define the touching point of the perpendicular from point B and PM. This point is point S. This is the right triangle BSM. In this right triangle BSM, this angle equals to 90 degrees minus alpha, this angle equals to 90 degrees, and therefore this first angle must be equal to alpha. According to the rule that says that the sum of the angles in the triangle is equal to 180 degrees. In the next step, we will prove that those two right triangles can go into each other according to angle side angle rule. According to angle side angle rule. This is the right triangle BSM. We prove that the right triangle BSM can go into this right lower triangle MNC according to angle side angle rule. So why those two right triangles can go into each other? First of all, those two angles are both equal to alpha and therefore they are equal to each other. In addition, those two hypotenuses of those two right triangles are both equal to 25 units and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So we prove that those two right triangles can go into each other according to angle side angle rule. That is to say, we actually prove that those two angles and the side that is included between those two angles, that is side BM on this right triangle BSM, are correspondingly equal to those two angles and the side that is included between those two angles, that is side MC and this side triangle MNC. Therefore, those two right triangles can go into each other according to angle side angle rule. So until now, if you found out that this is the right triangle BSM. And it converts. This is the sign converts to this right lower triangle MNC. according to angle side angle load. Again, we can find out that the upper right target BSM can went to the upper target MNC according to angle side angle load. And for the fact that those two right targets can go into each other, we will derive that those two corresponding sides must be also equal to each other and their lengths. According to the symbol, it states that congruent triangles in corresponding sides and congruent triangles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding sides must be also equal to each other and their lengths. But NC is 15, and therefore the corresponding side SM must be also equal to 15 units in itself according to the rule dimension. So what is the length of this mini-centimeter PS? From the drawing, it is very easy to see that PS in total equals to PM minus SM. So PS equals to PM minus SM. PS equals to PM, that is 25, minus SM, that is 15. So PS in total equals to 25 minus 15, that is 10. So PS equals to 10 units in its length. In this after AB SP, the opposite sides are equal to each other. That is to say, side PS equals to side AB. But PS is 10, and therefore the opposite side AB must be also equal to 10 units in its length. Okay. AB equals to 10 units in its length. So, if I know that AB equals to 10 units in its length according to the second method. And the answer to the question is that the perimeter of this quadrilateral ABCD is equal to 140 units in its length. So we finish to answer the first question. In the next step, I present to you the second question and answer the second question of this lecture. In the second question, our task is to find out the area of this green shape. Repeat again, in this second question, our task is to find out the area of this green shape. So in the drawing, we have two semicircles. This is the big semicircle. Inside this big semicircle, we have this small semicircle. In addition, we know that this is 9/7 AC, that equals to 4 units in its length. This is 9/7 CB, that equals to 6 units in its length. Again, our task is to find out the area of this green shape. From the drawing, it is very easy to see that the area of this green shape equals to the area of the big semicircle minus the area of the small semicircle. Okay. We define the center of this big semicircle. This point is point O. Likewise, we define the center of this small semicircle. This point is point S. we define the radius of this small semicircle as x. So the radius PS equals to x, and the radius SQ of this small semicircle also equals to x units in its length. The diameter of this big semicircle is AB. AB in total equals to AC, that is 4, plus CB, that is 6. So in total, the diameter AB of this big semicircle equals to 10 units in its length. AB equals to 4 plus 6, that is 10. We define the radius of this big semicircle as R. So the radius R must be equal to the diameter AB over 2. That is to say it is equal to 10 over 2. 10 over 2 is 5, so R equals to 5 units in its length. That is to say the radius of this big semicircle R equals to 5 units in its length. The only missing variable is the radius of this small semicircle. Once we find out the radius, we will find out the area of this green shape. Why? Because the area of the green shape equals to the area of this big semicircle, that is actually pi r squared, and r is 5, so it will be pi times 5 squared over 2. So it is pi r squared over 2, because of the fact that r is equals to 5. Will be equal to pi times 5 squared over 2 minus the area of this small semicircle, that is equals to pi x squared over 2. So x is the only missing variable in this question. This is the radius of this small semicircle. So the radius of this big semicircle r equals to 5. In the next step, we will join point C and S together by a straight line. We join point S and C together by a straight line. Point C is the point of tendency of tangent AB with this small semicircle. So point S is the center of this small semicircle, point C is the point of the small semicircle itself, and therefore SC is the radius of this small semicircle, is equals to x. The radius SC is equals to x. The radius SC is drawn to point C, that is the point of tendency of tangent AB with this small semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius CS. If AB is perpendicular to CS, it means that this angle equals to 90 degrees in its side. And this angle also equals to 90 degrees in its side according to rule 1. In the next step, we will do another construction. That is to say, from point P, we will draw perpendicular on AB. Again, from point P, we will draw perpendicular on AB. So, okay, this angle equals to 90 degrees on its side, and this angle also equals to 90 degrees on its side, according to our construction. We define the touching point of the perpendicular from point P and AB. This point is point M. What is the left? First of all, what is the definition of line 7 PM? Line 7 PM or line 7 MP is the tangent to this small semicircle at point P. Again, line 7 MP is the tangent to this small semicircle at point P. So here we can implement rule 1. Why? Because we have the radius CP that is equals to x. The radius CP of this small semicircle that is equals to x is drawn to point P, that is the point of tendency of tangent MP with this small semicircle. And now, you know, this radius that is drawn to the point of tendency, then tangent MP will be perpendicular to the radius PS. If MP is perpendicular to PS, it means that this angle equals to 90 degrees according to rule 1. So, in the small polynomial PS CM, we have 1, 2, 3 areas, and therefore this fourth missing area must be equal to 90 degrees inside. According to the rule, it says that the sum of the areas in any quadrilateral is equal to 360 degrees. So in quadrilateral PSMC, we have 4 areas, and therefore we can relate to quadrilateral PSCM as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle PSCM, side PS must be equal to the opposite side MC. But PS is x, and therefore the opposite side MC must be also equal to x units in its length. Likewise, according to the same rule, in the same rectangle PSCM, side SC must be equal to the opposite side PM. But SC equals to x, and therefore the opposite side PM must be also equal to x units in its length. What is the roof of this missing line 7? Line 7 AM. And again, what is the roof of this missing line 7? Line 7 AM. For the moment, it's very easy to see that AM total equals to AC minus MC. Again, AM equals to AC minus MC. So, I already know. Actually found out that AM in total equals to AC minus MC. So AM equals to AC. AC is 4 according to what is given as the equation, minus MC. MC is x. So to that, if you found out that AM equals to 4 minus x units in its length. In the next step, we will do a construction. That is to say, we will complete this big semicircle to a circle. So completed the semicircle to a circle. The next step, we will extend tangent PM by a straight line until it touches the circle. And we will define the touching point of the extended tangent PM with this circle. This point is point N. PM is a tangent to this small semicircle, so PM is a tangent, it is absolutely a straight line. And when you extend a straight line by a straight line, the result PN must be also a straight line. So PN is also a straight line. If we focus on the right side of the straight line PN, it's point M. Here the sum of the areas must be equal to 180 degrees according to all three. Repeat quickly on all three. According to all three, the sum of the areas from one side of a straight line is equal to 180 degrees. So we check as at the right side of the third line Pn at point M, we have this angle that is right angle, plus this facing angle, so that the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this facing angle must be equal to 90 degrees in its size according to all three. So we know that point O is the center of this big semicircle. So from point O we have perpendicular OM on chord Pn. Again, from point O, that is the center of this big circle, we have perpendicular OM on chord Pn. And according to rule 15, a perpendicular from the center of a circle towards any chord bisects the chord. Page 15 on rule 15. According to rule 15, a perpendicular from the center of a circle to any chord bisects the chord. In the drawing, you have a circle. This is point S, that is the center of this circle. From point S, we have perpendicular ST on chord MN. And according to this rule 15, perpendicular ST bisects chord MN. That is to say, perpendicular ST divides chord MN into two halves. The first half is MT. Again, the first half of Mn is MT, and it of course equals to the second half of Mn, that is Tn, and each half has to be equal to Mn over 2 because Mn is bisected into two halves. So we can implement rule 15 in our drawing. In our drawing, so as I mentioned before, from the center of this big circle, that is to say from point O, we have perpendicular OM on chord Pm. Again, from point O, we have perpendicular OM on chord Pn. According to rule 15, perpendicular OM bisects chord Pn. That is to say, at point M, perpendicular Pn, at point M, chord Pn is being bisected into two halves. The first half is Pm, and it of course must be equal to the second half Mn. So Pm, that is the first half of Pn, equals to Mn, that is the second half of Pn. So Pm equals to Mn according to rule 15. But we already found out that Pm equals to x. So we can write there that Pm equals to x, and from this equation x equals to Pm equals to Mn, we derive that Mn also equal to x units in its length. This is, let me see now, Mn is equals to x units in its length. In the next step, we will implement rule 24 in our drawing. So on page 15 on rule 24. Rule 24 is true in any circle. So in any circle, if chord AB intersects with chord CD at point O, then the following equation is true. That AO times BO equals to CO times DO. So in the drawing we have a circle. This is chord AB that intersects with chord CD at point O. Again, chord AB intersects with chord CD at point O. In this drawing, the following equation is true. That AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can implement rule 24 in our drawing. In our drawing, we have chord AB, that is the diameter of this big semicircle. Chord AB intersects with chord Pn at point M. Again, chord AB intersects with chord Pn at point M. So all the requirements of rule 24 are satisfied, and therefore we can implement rule 24. So, I don't know if you know that now we are drawing chord AB intersects with chord Pn 0.10. Therefore, we can measure all 24. According to all 24, the following equation is true. AM times MB equals to PM times MN. But again, according to all 24, the following equation is true. AM times MB equals to PM times MN. AM is 4 minus X. Times MB. MB in total equals to X plus 6. And this equals to PM. PM is X times MN. MN is also X. So PM times MN is X times X, that is X squared. So in total, if you found out that four minus X times X plus 6 equals to X squared. Here we will open the brackets on this side of the equation and we get that 4 times X is 4X, and we have 4 times 6 is plus 24, minus X times X is minus X squared, and we have minus X plus 6 is minus X, 6X, equals to X squared. Here we have 6X minus 4X minus 6X is minus 2X. We have also plus 24 minus X squared equals to X squared. So here we add X squared to the equation and finally get that here X squared minus X squared is 0. So in this side of the equation we left only minus 2X plus 24 equals to X squared plus X squared is 2X squared. Here we subtract 2x from the equation, and finally we get that in this side of the equation we left only with 24 equals to 2x squared plus 2x. And again, if you find out in total that 24 equals to 2x squared plus 2x. Here we will subtract 24 from this equation and finally we get that 2x squared plus 2x minus 24 equals to 0. So here we divide this equation by 2 and finally get that 2x squared over 2 is x squared plus 2x over 2 is x plus x minus 24 over 2 is minus 12 equals to 0 over 2 is 0. So in total, if you found out that x squared plus x minus 12 equals to 0. So actually this is a quadratic equation, and the general formula for quadratic equation is as follows. ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of the quadratic equation, and x is the value that we are looking for. And we find out the value of x according to the following formula: x equals to minus b plus minus square root of b squared minus 4 times a times c divided by 2a. Again, minus b plus minus square root of b squared minus 4 times a times c divided by 2a. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. Now, specific quadratic equation, that is to say x squared plus x minus 2f equals to 0. The variable that we are looking for is x. X is the radius of this small semicircle. X is the radius of the small semicircle. The coefficient A in our specific quadratic equation, this equation, the coefficient A equals to 1, the coefficient B also equals to 1, and finally the coefficient C equals to minus 12. And X is the radius of the small semicircle. So the only thing that is left to do in order to find out the value of X, that is the radius of the small semicircle, is to put this data of our specific quadratic equation inside this general formula for x. In this way, we find out the value of the values of x, that is the values of the small semicircle. So copy again the general formula for x. X equals to minus b plus minus square root of b squared plus 4 times a times c over 2a. So we put the data of our specific quadratic equation inside this general formula for x. In this way we find out the value of x, that is the radius of the small semicircle. We do it now, we get that x equals to minus b. B is 1, so minus b is minus 1, plus minus square root of b squared. B is 1, so b squared is 1 squared, it is 1, minus 4 times a times c. So it is minus 4 times a is also, it is minus 4 times 1, that is minus 4 times c. C is minus 12, so minus 4 times 12 is plus 48. So in total inside the root we have 1 plus 48 over 2a. A is 1, so 2a is 2 times 1, that is 2. So in total we should find out that x equals to minus 1 plus minus 1 plus 48 is 49 over 2. So x equals to minus 1 plus minus square root of 47, square root of 49 is 7 divided by 2. So do that if you follow that x equals to minus 1 plus minus 7 over 2. So here we have two solutions that are possible for x. The first solution for x is that x equals to minus 1 minus 7 over 2. Minus 1 minus 7 is minus 8, and minus 8 over 2 is minus 4. So according to the first solution for x equals to minus 4. But x can never be equal to minus 4 because x is the radius of this small semicircle. That is to say, x is a length, and the length must be a positive number. And therefore, x can never be equal to minus 4, that is a negative number, so we can set the first solution for x, and we take into account only the second solution for x. The second solution for x is as follows. X equals to minus 1 plus 7 over 2. Minus 1 plus 7 is 6, and 6 over 2 is 3. So if you know that the radius of the small semicircle x equals to 3, our task is to find out the area of this green shape. What is the area of the green shape? The area of the green shape, it is equal to the area of the big semicircle minus the area of the small semicircle. So the area of the green shape in total is equal to the area of the big semicircle with radius 5 minus the area of this small semicircle with radius 3. So what is the area of the green shape? The area of the green shape in total equals to the area of this big semicircle with radius 5. The area of any semicircle equals to pi r square over 2. R is 5, so it is pi times 5 square over 2 minus the area of the small semicircle with radius 3. So the area of the small semicircle must be equal to pi times 3 square over 2. Here we take 2 as a common factor out of those two expressions. So in the denominator we have 2. In the numerator of this expression we have in total 25 pi minus in the numerator of this expression we have in total minus 9 pi. 25 pi minus 9 pi is 16 pi. In total, this expression equals to 16 pi over 2. That is 8 pi. In terms of numbers, it is equal to 25.13 square units in size. Then again, if you found out that the area that we're looking for this question, that is the area of this green shape, it is equal to either 8 pi square units in size, or in terms of numbers, it is equal to 25.13 square units in size. So finish to answer the second question. In the next step, as summarize the lecture, that is to say, we will repeat on the solution of the first question, and then we repeat on the solution of this second question. So we start with the first question. In the first question, our test was to find out the area of this quadrangle ABCD. Our test was to find out the perimeter of this quadrangle ABCD. What is the perimeter? The perimeter of a quadrangle is the sum of its four side lengths. That is to say, the perimeter of this quadrangle ABCD equals to AB plus AD plus DC plus CB. So it has given us the question that this is line 7 PQ that equals to 10 units in its length. This is line 7 PQ that is equals to 20 units in its length. This is line 7 QC that equals to 40 units in its length. Those three angles are all right angles. Again, our task is to find out the perimeter of this quadrangle ABCD. It is actually the sum of its four side lengths. So in the first step, we did a construction, that is to say, we drew perpendicular on AD at point P. Again, we drew perpendicular on side AD at point P. So this angle equals to 90 degrees inside, and this angle also equals to 90 degrees inside according to our construction. In the next step, we extended the perpendicular from point P until it touches side BC. And we define the touching point of the extended perpendicular from point P and BC. This point is point M. Those two angles are defined as one-sided interangles. The sum of those two one-sided interangles is equal to 180 degrees, and therefore they must be located between parallel lines. That is to say, AB is parallel to PM according to Rule 18. And again, if you found out that AB is parallel to PM according to Rule 18. Likewise, the sum of those two one-sided interangles is also equal to 180 degrees, and therefore those two one-sided interangles must be located between parallel lines. That is to say, PM is parallel to the opposite side DC. According to the sum rule, Rule 18. Again, PM is parallel to DC according to Rule 18. Likewise, the sum of those two one-sided interangles is also equal to 180 degrees, and therefore those two one-sided interangles must be located between parallel lines. That is to say, AB is parallel to DC. Again, AB is parallel to DC according to the sum rule, Rule 18. So in total, in conclusion, we found out that those three line segments AB and PM and DC are all parallel to each other according to Rule 18. So we have three parallel lines. AB is parallel to PM, which is parallel to DC. This is line 7 AD connects the three parallel lines together. Likewise, line 7 BC also connects the three parallel lines together. And according to the basic proportionality theorem, a special relationship exists between AD and BC that connects those three parallel lines together. The relationship is as follows. AP over PD equals to BM over MC. AP over PD equals to BM over MC. It is given us a question that AP equals to PD. So if we define the length of AP as X, then PD must be also equal to X because they are equal to each other according to what is given us the question. So AP over PD is X over X. Yeah, AP over PD is X over X, and it is equals to BM over MC. X over X is 1, so 1 equals to BM over MC. Even multiply this equation by MC, and find out that MC equals to BM, or BM equals to MC. BM equals to MC. Point M is the midpoint of BC. It's point M. BC, side BC is bisected into two halves. The first half is BM. The first half of BC is BM, and it is of course equal to the second half of BC, that is MC. Each half must be equal to BC over 2 because BC has been bisected into two halves. And again, the first half of BC is BM. It is of course equals to the second half of BC, that is MC. and each half must be equal to BC over 2 because BC is intersected into two halves. BC in total equals to 10 plus 40, this is 50. Yeah, BC equals to 10 plus 40, it is 50, and 50 over 2 is 25. And from this long equation, we write that BM equals to MC equals to 25. That is to say, BM equals to 25 and MC also equals to 25 units in its length. In the next step, we have here BM, this is answer at BM, this is equals to 25 units in its length. This is answer at BQ, this is equals to 10 units in its length. QM in total must be equal to BM minus BQ. Again, QM equals to BM minus BQ. So QM equals to BM. BM is 25 minus BQ, that is 10. So in total, QM equals to 25 minus 10, that is 15. This is the answer at QM, that is equals to 15 units in its length. In the next step, we implemented the Pythagoras theorem on this red triangle PQM. According to the Pythagoras theorem, in a triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this triangle PQM, PM squared, that is the square of the hypotenuse, equals to QM squared plus QP squared. Again, in the right triangle PQM, here by PT is information for Pythagoras theorem. So in the right triangle QPM, PM squared, that is the square of the hypotenuse, equals to QM squared plus PQ squared. PM is the missing side, so we will test it is, so it is PM squared equals to QM squared. QM is 15, and therefore QM squared is 15 squared, that is 225, plus QP squared. QP is 20, and therefore QP squared is 20 squared, that is 400. So the total function 400 PM squared equals to 225 plus 400, that is 625. So PM squared equals to 625. Here we took out all the equation, and 400 PM equals to the square root of 625, that is 25. So this is the missing hypotenuse PM, that is equals to 25 units in its length. In the next step, we did another construction, that is to say from point M, we draw perpendicular on DC. Again, from point M, we draw perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees. This angle also equals to 90 degrees according to the construction. We define the touching point of the perpendicular from point M and DC. This point is point N. When we do this construction, we can do quadrilateral PM and D. Inside quadrilateral PM and D, we have 1, 2, 3 degrees. The sum of 3 degrees is 270 degrees. So 270 degrees plus the size of this 4 pieces again, in total must be equal to 360 degrees. According to a rule that says that the sum of degrees in any quadrilateral is equal to 360 degrees. And therefore this 4 pieces again must be equal to 90 degrees in size. So in quadrilateral PM and D we have 4 degrees, and therefore quadrilateral PM and D is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle PM and D, side PM must be equal to the opposite side DN. But PM is 25, and therefore the opposite side DN must be also equal to 25 units in its length. In the next step, we define this angle QPM as alpha. So in the given angle PQM, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles in a triangle. BC, this is side BC. BC is one side of quadrilateral ABCD, and therefore it is absolutely a straight line. So if we focus on the left side of the straight line BC here at point M, and so here the sum of the angles must be equal to 180 degrees according to all three. All three said that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the left side of the straight line BC at point M? We have this angle that is equal to 90 degrees also, plus this angle that is equal to 90 degrees, plus this missing angle, so that must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to alpha. Why? Because here we have 90 degrees minus alpha plus 90 degrees, and 180 degrees minus alpha. So 180 degrees minus alpha plus alpha, it is equal to 180 degrees. It is the sum of the angles of the left side of the straight line BC at point M according to rule 3. Therefore, this BC angle must be equal to alpha. So in the right lower triangle M and C, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first BC angle must be equal to 90 degrees minus alpha. According to the rule that said that the sum of the angles in this triangle is equal to 180 degrees. In the next step, prove that those two triangles can join to each other according to angle side angle rule. That is to say, prove that this is again right triangle PQM, that it can join to this right triangle M and D according to angle side angle rules. Angle side angle rule. So what those two right triangles can join to each other? First of all, those two angles are both equal to alpha, and therefore they are equal to each other. In addition, those two angles are both equal to alpha, and therefore they are equal to each other. In addition, those are the hypotenuses of those two right angles. They are both equal to 25 units, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So we found out that those two right angles can join to each other according to angle side angle rule. That is to say, we can prove that those two angles and the side that is included between those two angles, that is side PM, this again right triangle PQM, are corresponding equal to those two angles, and the side that is included between those two angles on this that is the side that is included between those two angles, that is side MD, this right lower triangle M and D. And therefore, those two right triangles can join to each other according to angle side angle rule. And again, if you found out that the upper plane triangle QPM can join, this is the sign of can join to the right lower triangle M and C according to angle side angle rule. And from the fact that those two right triangles can join to each other, we know that those two corresponding sides must be also equal to each other and their lengths. According to the rule that corresponding sides and congruent triangles are equal to each other. Those two triangles can join to each other, and therefore those two corresponding sides must be also equal to each other and their lengths. But QP is 20, and therefore the corresponding side MN must be also equal to 20 units in its length. Likewise, those two corresponding sides must be also equal to each other in their lengths according to the sum rule. But we know that SM, again, those two corresponding sides must be also equal to each other in their lengths according to the sum rule. But BM, those two corresponding sides must be also equal to each other in their lengths according to the rules I mentioned. But QM is 15, and therefore the corresponding side NC must be also equal to 15 units in its length. So in total, DC equals to 25 plus 15, that is 40. AB is the missing side. So we only found out that PM and D is the rectangle. But we also know that the opposite sides of the rectangle are equal to each other. So in rectangle PM and D, side MN must be equal to the opposite side PD. But MN is 20, and therefore the opposite side PD is equals to X equals to 20 units in itself. Likewise, here AP equals to X and X equals to 20 units in its length. AB is the only missing side. We found out the side of AB by implementing the basic, by implementing the trapezoid mid-symmetry in our drawing. First of all, quadrilateral ABCD is a trapezoid. Why quadrilateral ABCD is a trapezoid? Because it has one pair of parallel sides. Side AB is parallel to the opposite side DC, according to rule 18. And therefore trapezoid ABC, and therefore quadrilateral ABCD is a trapezoid. The two parallel sides, that is to say AB and DC, are defined as the bases of this trapezoid ABCD, while the two other sides that are not parallel to each other, that is to say AD and BC, are defined as the legs of this trapezoid ABCD. This is line segment PM. Line segment PM bisects both legs AD and BC. Line segment PM bisects side AD because it divides side AD into two halves. The first half is AP, that is 20, and it is equal to the second half of AD, that is PD, that is also 20. Likewise, 9:07 p.m. bisect also the leg BC. That is to say, 9:07 p.m. bisect the leg BC into two halves. M is the midpoint of BC, so at point M, the leg BC has been bisected into two halves. That is to say, the first half of BC is BM, this is 25, and it is of course equals to the second half of BC, that is MC, that is also 25. So, in conclusion, you can say that 9:07 p.m. bisects both legs AD and BC, and therefore 9:07 p.m. is defined as the mid-segment of trapezoid ABCD. What is the length of this mid-segment PM? According to the trapezoid mid-segment theorem, PM in total equals to AB plus DC, that is the sum of the two parallel bases of trapezoid ABCD over 2. So, according to the trapezoid mid-segment theorem, the length of the mid-segment PM equals to the sum of the two parallel bases of trapezoid ABCD, that is actually AB plus DC over 2. But we already found out that PM equals to 25, so PM equals to 25, AB is the missing side, so leave it as it is, plus DC, DC in total equals to 25 plus 15, that is 40. Again, PM is 25, AB is the missing side, DC is 40 divided by 2. So in total we found out that 25 equals to AB plus 40 over 2. Here we multiply this equation by 2 and found out that 25 times 2 is 50, so 50 equals to AB plus 40. Here we subtract 40 from this equation and found out that the missing side AB equals to 10 units in its length. 50 minus 40 is 10, so AB equals to 10. This is the missing side AB, it equals to 10 units in its length. Our task is to find out the perimeter of this quadrilateral ABCD. We know that the perimeter of any quadrilateral is equal to the sum of its four side lengths. That is to say, it is equal to AB plus AD plus DC plus CB. So the perimeter of quadrilateral ABCD in total it is equal to the sum of its four side lengths. That is to say, it is AB plus AD plus DC plus CB. AB is 10 plus AD is 40 plus DC is also 40 and CB is 50. So in total the perimeter of quadrilateral ABCD equals to 10 plus 40 plus 40 plus 50, that is 140 units in its length. And again, if we found out that the perimeter of this quadrilateral ABCD is equal to 140 units in its length. In the next step, I presented to you a second method to find out that AB is 10. According to the first method, we relied on the basic trapezoid mid-segment theorem in order to find out that AB is 10. In the second method, we did another thing, that is to say, from point B we draw perpendicular on PM. So this angle equals to 90 degrees inside, and this angle also equals to 90 degrees inside according to our construction. We define the touching point of the perpendicular from point B and PM. This point is point S. So in quadrilateral ABSP, we have 1, 2, 3 right angles, and therefore this fourth angle must equal to 90 degrees inside, according to the rule that said that the sum of the angles in any quadrilateral is equal to 360 degrees. So in quadrilateral ABPS we have 4 angles, and therefore quadrilateral ABPS is a rectangle. So in this either BSM, this angle equals to 90 degrees one point, this angle equals to 90 degrees, and therefore this angle must equal to alpha according to the sum that I already mentioned a couple of times ago, that the sum of the angles in a triangle is equal to 180 degrees. So in the next step we prove that those two right angles can point to each other according to angle sine angle rule. That is to say, we prove that this right angle BSM can point to this right angle M and C according to angle sine angle rule. So why those two right angles can point to each other? First of all, those two angles are both equal to alpha and therefore they are equal to each other. In addition, the hypotenuse of those two right angles are both equal to 25 units and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So we can prove that those two right triangles can point to each other according to angle, side, angle, rule. That is to say, we actually prove that those two angles and the side that is included between those two angles, that is side BM, this right triangle BSM corresponds equal to those two angles, and the side that is included that between those two angles, that is side MC, this right lower triangle, triangle MNC. And therefore, those two right triangles can point to each other according to angle, side, angle, rule. Repeat again, if you found out that the after right triangle BSM can point to the right lower triangle MNC according to angle, side, angle, rule. And from the fact that those two right triangles can point to each other, we derive that their corresponding sides, that is to say SM and NC, must be also equal to each other and their lengths. But NC is 15, and therefore its corresponding side SM must be also equal to 15 units in its length. What is the length of this piece and PS? PS in total equals to PM minus SM. And again, PS equals to PM minus SM. So PS equals to PM, that is 25, minus SM, that is 15. So in total, PS equals to 25 minus 15, that is 10. So PS equals to 10 units in itself. So in rectangle ABSP, side PS must be equal to the opposite side AB, but PS is 10, and therefore the opposite side AB must be also equal to 10 units in itself. So we found out in two different methods that AB equals to 10. And the answer to the question is that the perimeter of this quadrilateral ABCD equals to 140 units in its length. So we finish to repeat on the first question, the solution of the first question. In the next step, I repeat on the solution of the second question. In this second question, our task is to find out the area of this main shape. So, in the drawing we have two semicircles. This is the big semicircle. Inside this big semicircle, we have this small semicircle. In addition, we know that this is line segment AC, this is equals to 4 units in its length. This is line segment CB, this is equals to 6 units in its length. Again, our task is to find out the area of this main shape. So, in the first step, we define the center of this big semicircle. This point is point O. We define the center of this small semicircle. This point is point S. We define the radius of this small semicircle is Sx. So the radius of SP equals to X, the radius of SQ also equals to X. And we know that the diameter of this big semicircle is AB. The diameter AB in total equals to AC, that is 4, plus CB, that is 6. So in total, the diameter AB equals to 4 plus 6, that is 10. We define the radius of this big semicircle as R. So the radius R must be equal to the diameter AB over 2. That is to say, it is 10 over 2, that is 5. So in total, we have found out that the radius of this big semicircle is equal to 5 units in its length. In the next step, we join points S and C together by straight line. Point S is the center of this small semicircle, point C is the point on the small semicircle itself, therefore AC is the radius of this small semicircle, that is equals to X. So here we can implement rule 1, because we have the radius SC is equals to X, the radius SC is going to point C, that is the point of tendency AB with this small semicircle. And whenever your radius is going to the point of tendency, then tangent AB will be perpendicular to the radius CS. If AB is perpendicular to CS, it means that this angle equals to 90 degrees in size, and this angle also equals to 90 degrees in size according to rule 1. In the next step, we did another construction, that is to say, for point P, we go perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the tangent point of the perpendicular for point P and AB. This point is point M. But doing so what is the definition of line segment MP? MP is the tangent to this small semicircle at point P. So if we can implement rule 1. Why? Because we have the radius SC of this small semicircle that equals to X, the radius SC the radius SP is equal to x, the radius of SP is 1 to point P. That is the point of tendency of tangent MP with this small semicircle. And whenever you have a radius that is 1 to the point of tendency, then MP will be perpendicular to the radius SP. If MP is perpendicular to SP, it means that this is equals to 90 degrees according to all 1. So in total, in the small quadrilateral PSCM, we have 1, 2, 3 integers, and therefore this 4 integers must be equal to 90 degrees inside. So quadrilateral PSCM is 4 integers, and therefore quadrilateral PS can relate to quadrilateral PSCM as a rectangle because it has 4 integers. But we also know that the opposite sides of the rectangle are equal to each other. So in the small rectangle PSCM, side PS must be equal to the opposite side MC, but PS is x, and therefore the opposite side MC must be also equal to x units in its length. Likewise, according to the sum rule, in the small rectangle PSCM, side SC must be equal to the opposite side PM, but SC is x, therefore the opposite side PM must be also equal to x units in its length. So if you found out that quadrilateral PSCM is not a rectangle, but a square, by because of the fact that all of its sides are equal to each other, its side is equal to x. So, what is the length of this missing 970 AM? AM equals to AC, that is 4, minus MC, that is x. So in total, again, AM equals to AC minus MC. So AM equals to AC, that is 4, minus MC, that is x. So in total, AM equals to 4 minus x units in its length. In the next step, we did the construction, that is to say, we completed this big semicircle to a circle, and then we extended tangent PM by third line until it touches the circle at this point. We define the touching point of the extended tangent PM with this circle. This point is point N. When you extend the third line by third line, PN is a tangent, and therefore it is a third line. When you extend the tangent PM by third line, the result PN must be also a third line. So we know that PM is a third line. If we focus on the right side of the third line PM, it's point M. Here the sum of negatives must be equal to 180 degrees according to all three. All three says that the sum of negatives from one side of the third line is equal to 180 degrees. So which angles we have in the right side of the third line PN, it's point M. We have this angle. This was to 90 degrees inside, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees inside. So, point O is the center of this big semicircle. For point O, we have perpendicular OM on chord PN. Again, we have here perpendicular OM on chord PN, and according to rule 15, a perpendicular from the center of a circle towards any chord bisect the chord. So according to rule 15, perpendicular OM, that is one from point O, that is the center of this big semicircle, perpendicular OM bisect chord PN. That is to say, at point M, chord PN is being divided into two halves. The first half is PM, and it is also of course equal to the second half of PN, that is MN. According to rule 15, PM equals to MN. But PM is x, so we can enter that PM is x, and from this equation x equals to PM equals to MN, we will derive that MN also equals to 5 units in MN also equals to x units in its length. This is not MN, this is equal to x units in its length. In the next step, we implemented rule 24 in our drawing. So, a big picture on rule 24. According to rule 24 is true in any circle. So in any circle, if chord AB intersects with chord CD at point O, then the following equation is true. That AO times OB equals to CO times OB. So in the drawing we have a circle, this is chord AB that intersects with chord CD at point O. So in this drawing, the following equation is true. That AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can actually implement rule 24 in our drawing. Why? Because in our drawing we have chord AB, and it's actually the diameter of this big semicircle or big circle. So chord AB intersects with chord PN at point M. Again, chord AB intersects with chord PN at point M. So again, in our original drawing, we have chord AB that intersects with chord PN at point M. So all the requirements of all 24 are satisfied, and therefore we can implement all 24. According to all 24, the following equation is true that AM times MB equals to PN, AM times MB equals to PM times MN. Again, according to all 24, AM times MB equals to PM times MN. Here we have, what is the ref of AM? AM in total equals to AC minus MC. AC is 4, MC is X, so in total AM equals to 4 minus X. So here, substitute AM by 4 minus X times MB. MB in total equals to X plus 6. So substitute MB by X plus 6, and it is equal to PM times MN. PM is X. Mn is also x, so PM times Mn is x times x, that is x squared. So in total, according to all 24, we should find out that 4 minus x times x plus 6 equals to x squared. Here we open the brackets of this expression and find out that 4 times x is 4x, plus 4 times 6 is 24, minus x times x is minus x squared. And finally we have minus x times 6, that is 6x. And it is equals to x squared. Here we have 4x minus 6x is minus 2x, plus 24 minus x squared equals to x squared. Here we added x squared to the equation, minus x squared plus x squared is 0, so in this side of the equation we have to leave minus 2x plus 24, while in the other side of the equation we have x squared plus x squared, that is 2x squared. So in total we should find out that 2x plus 24 equals to 2x squared. Here we added 2x to this equation, and finally found out actually that 24 equals to 2x squared plus 2x. Here we subtracted 24 from this equation, and finally found out the 2x squared plus 2x minus 24 equals to 0. Here we divided this equation by 2, and finally found out that 2x squared over 2 is x squared, plus 2x over 2 is x, minus 24 over 2 is minus 12, equals to 0 over 2 is 0. So in total we found out that x squared plus x minus 12 equals to 0. This is the quadratic equation, and the general formula for a quadratic equation is as follows: ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula: x equals to minus b plus minus 4 to b squared minus 4 times a times c over 2a. So, in our specific quadratic equation, that is to say x squared plus x minus 12 equals to 0, the variable that we are looking for is x. And x is the radius of this small semicircle. The coefficient a equals to 1, the coefficient b also equals to 1, and the coefficient c equals to minus 12. So the only thing that is left to do is to put the data of our specific quadratic equation inside this general formula for x. In this way, we find out the value of the values of x, that is the values of this small semicircle. The general formula for x is x equals to minus b plus minus 4 of b squared minus 4 times a times c over 2a. So actually we put all the data for our specific quadratic equation inside this general formula for x, and found out that x equals to minus b. B is 1, so minus b is 1 plus minus 4 of b squared. B is 1, so b squared is 1 squared, that is 1, minus 4 times a times c. So it is minus 4 times a is 1, so minus 4 times 1 is minus 4 times c. C is minus 12, so minus 4 times minus 12 is plus 48. So inside out we have 1 plus 48 divided by 2a. A is 1, so 2 times a It's 2 times 1, that is 2. 1 plus 48 is 49, so in total we found out that x is equals to minus 1 plus minus square root of 49 over 2. The square root of 49 is 7, so in total we found out that x equals to minus 1 plus minus 7 over 2. So here we have two solutions that are possible for x. The first solution for x is that x equals to minus 1 minus 7 over 2. Minus 1 minus 7 is minus 8, and minus 8 over 2 is minus 4. So the first solution for x is that x equals to minus 4. But x can never be equal to minus 4 because x is the radius of this small semicircle. So x is a length, and x as a length, it must be a positive number. It must be a positive number. It can never be equal to minus 4. That is a negative number. So we cancel the first solution. Cancel the first solution for x, and we took into account only the second solution for x. The second solution for x is as follows: x equals to minus 1 plus 7 over 2. Minus 1 plus 7 is 6, and 6 over 2 is 3. So if we found out that the radius of this small semicircle, x equals to 4 units in its length. Again, our task is to find out the area of this green shape. From the drawing, it is very easy to see that the area of the green shape in total equals to the area of the big semicircle plus the area of the small semicircle. Again, the area of this green shape in total must be equal to the area of the big semicircle plus the area of this small semicircle. We know that the radius of the big semicircle is 5, so in total the area of the big semicircle must be equal to pi times 5 square over 2 minus the area of the small semicircle with radius 3. So if the radius 3, then the area must be equal to pi times 3 square over 2. Again, the area of the small semicircle equals to pi times 3 square over 2. Here we took 2 as a common factor out of those two expressions. So the numerator we have 2. Well, in the numerator of this expression, in total we have 25 pi minus pi times 3 square is minus 9 pi over 2. Here we have 25 pi minus 9 pi is 16 pi, and 16 pi over 2 is 8 pi. So in total, we should find out that the area of this green shape, that is the area that we're looking for in this question, it is equal to either 8 pi square units in size, or in terms of numbers, it is equal to 25.13 square units in size. Okay, thank you very much.